Welcome back. Alrighty, so we will continue now with our lab. This is the lab for session 2. I'm sharing my screen again, and I have R open here already, and I have here the lab assignment open. So this will be posted. So today, I will actually post it today already, although I mentioned it will only be tomorrow. But the clock will be starting to tick tomorrow, which means this will be due within a week. That would render it to be due on actually the 13th at midnight. Gives you an additional day, right? Half a day. 1 p.m. Okay, so it's a super simple lab. You will see, I hope all of you have gotten a handle on DataCamp. This is working now. You have now a basic idea on how to look at objects, how to treat objects, how to look at vectors and peg vectors in objects, get vectors out of multi-dimensional objects. So I think there are various things that DataCamp will show you pretty quickly. If any questions, please post them to the discussion board. I can't emphasize it enough how important the discussion board is for an online class. And the same with questions concerning the lab assignments. So the idea with that is really, if you have questions, post them to the discussion board and let your colleagues help you. I'm obviously also going to be there. I'm going to be hovering around and I'm going to be helping you as soon as I see this is pending too long. I'll try to be super responsive. You can also write to me directly, that's fine, but I will ask you to also post your question and my response to the discussion board, because it's generally important knowledge, right? Everything we discuss here could be helpful for one of your colleagues as well, so it's kind of you're depriving them from this response and from this discussion. So I'd really encourage you to post on the discussion board. Okay. So what we're doing, so this is the assignment that is posted for this week. So this is assignment for lab 2, due September 13. So that's Monday next week. This is also the time point where I post already the next lecture. So this will come out Monday morning. And okay. So what do we have? So we're importing a Sas data set. As you can imagine, with like every other software, R is very dependent on their own kind of data structures, but it also allows us packages to kind of gain a little bit of versatility, which is actually super, super helpful. So you can, for example, with a library called Sas7B.dat, you can actually read Sas files into R. There's considerably little problems with that. There are some problems with some data files occasionally, particularly when it comes to multidimensional data files and large data files and data files with some certain data structures within SAS. And in case you run into problems, and I mentioned it, you can use the Haven library as well. So we will also do this as an alternative approach. Good. Let's talk about this. We will be trying this out. I'm actually going to be walking you through that part of this assignment. Then question 2, we will talk about this, how to write tables from R, how to export them into TXT files, how to import these again, how to use them for summary statistics for I think we talked about this very briefly. Then we're going to draw some scatter plots and we will build a linear model. Then we're going to look into some model parameters. Okay, good. What are we doing? So let's open the script and let's do the SAS portion of it first, because it also comes here first. So as said, so we're doing question 1. Question 1, which is the French mail data set. So you know already that you can always hashtag things out. The most important thing for R programming and every other program for that matter is documenting. Comment, 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 comment. You need to understand what each line means and you need to comment what each of your lines that you created means. So you're supporting your future self, because if you have to revisit your code in a year from now, you will not remember all of these lines that you've created, particularly when it gets considerably complex. You will have issues to do that. Trust me, it will be not easy. Okay, so now we said library Sas7 debug, library Sas7 that. So in case you don't have it installed, you go on packages, you click on install, and you find here in the repository for Sas7 that. This is the library you want to install. You just click on install, it will install all the dependencies. You have that library installed. I have it installed already, so I'm not going to repeat that exercise. So now we basically have this installed. So now, if you want to read now the French data set, what do you need to do first? You need to understand where is it located. So where is it located? We talked about, please create a folder on your desktop. Always make it easily accessible on your desktop. Click on the respective folder, click on the file that you want to export. And click on option when you're in the actual menu and copy it as a path name. If you click option, it will automatically give you the path name. So if you're writing, okay, you can now do a couple of different directory. So I usually what I do is I create entries for whatever data file I'm looking at. So I call this read.directory. I create an object that contains the exact path name to wherever I want to go. So this read.directory contains now the path to that file. So you can also you can also amalgamate this, obviously, and you can do. Oops, not good. Okay, so this is read.directory. You can also put this together and say, okay, you put the file name extra. You can call it read.filename. And why is this important? This is important because you can then down the road save yourself a lot of headache. So you got to put it on a quotation mark. That's how you get it separated. And now you can essentially you can do read there dot file name. You can call this now C. With C you concatenate things. You can do read.directory, comma, read.filename. Should give you now essentially an overall. Paste. So with paste, you can actually make this. You can put this together. So the separation. You can avoid any spaces in between. Okay. Good. There's a bracket missing. Okay. Oh. Okay. That should have worked. So as you can see, okay. Okay, so what do we do? Let's review this. So we have now library, we loaded the library. We have read.directory, which is essentially the directory that leads to that lab, to that file, which we have in a separate object. We have here just the file name in the object. Here we have the directory in the object. Now we're putting this together with C paste. I don't even think we need the C. Well, let's try that. That should have worked just fine as well. Okay, good. So we don't need to see. Okay, so we paste to paste read directory, we paste read file name, separate equals blanks, so no space. But that essentially pushes it together. Otherwise, it would create a space. So you can also, if you leave it blank, I think it creates one space in between this object, which contains the directory, and this object, which essentially contains the file name. So, and now we can essentially also look already at the function, which is now read.sas7bdat. So this is now a SAS database reader, which is part of this library. Read sas7bdat will read a file without debugging it. It will basically read whatever data you are giving it from SAS. So now read.sas7bdat. Now we want read.directory.file name. And this is already our data file, right? So now we want to pack this all in an object, right? So if we do df, we're packing this now in the df in a data frame. So here it is. This is our data file. All right. Good luck with the rest of the assignment. So this should be fairly easy from here on. Then I mentioned the Haven library. In case you ever run into issues with reading SAS files, you can also use a read underline SAS. Is this the one from Haven? I think this is the one from Haven. But there are a couple of different others. Haven, SAS. I think it's, yeah, read underlines was exactly, that's the one. Okay. So this is the same kind of command. Does the same thing, essentially. Let's call this df1. Let's read this in. Same story. The only problem here becomes a tibber, which needs to be untibbered, which is a little bit. But this also imports essentially the names, which now, if you do ls df1, you also get the secret df1 age. You get these, so you would need to separate them, remove them. So I suggest you use the read sas7bdat function, but this is a workaround that can be used in case it becomes necessary. So the problem is this becomes a so-called tibber, which is a little bit more complicated, which is a separate kind of format that is multidimensional, a little bit more complicated to address. Okay, so now back to our lab. So we want to now essentially look into how to treat data and how to get data out. So we have base R essentially has basic data sets at their disposition. One of them is cars. So if we load a data set, so you can do data empty cars. But this is for the other questions. So this is now actually. So if we do data empty cars, This is an internal kind of data set that will now load a data set into empty cars. So now we have empty cars available. So this is loaded now. If we're looking at the dimensions of empty cars, so we have here with dim, we can look at the dimensions. So we have here for each car that has been of interest for this data set, over some point we have all kinds of different information that has been relevant. So we have 6 number of cylinders, we have the miles per hours, we have suspension, horsepower. I don't know what all of this means. I'm not really a car guy. Lived too long in the I don't know much about cars at this point. Haven't owned a car in like 15 years. Okay, so we have now the dimensions of cars will be assessed with dim. So 32 by 11 means we have 32 rows. Just like we address each of those cells with everything before the comma, so always first is the row and second part is always the column. Here we have 32 rows over 11 columns. So these are the dimensions of our empty cars. So another way to look at this is essentially to do head. So we know head empty cars will always kind of show the first 6 entries, right? You can also change the number. You can do head 10, and it will give you the first 10. But the default of head is 6. Equally, you can also do tails. Tail, not head and tails. It's tail. Tail gives you the last 6 entries. Equally, it can be manipulated to show you the last 10 or 20, as many as you want. So now what do we want to show next? So we want to now, and this is part of the assignment, we want to export the name of the dimension, the name of the variable. So if we are now so we want to save this now as a text file. So if we want to do, we have it written here, so using write.table. So if we're writing write.table, empty cars, in a file, that is called paste. And here we're pasting again, right? If we paste read starts directory, oh no, wait, hold on. So now we do, now we're rewriting this. And that's another tip I give you guys. So, okay, so you have now, this is the raw directory. This is the directory which essentially contains the files that I have given you. If you are opening now a second folder and you call this the right folder, let's call it output. Let's call it output. And then you also have an R&D file. Oh yeah, so here we actually have code. Okay, good. Okay, we can look at this later. Okay, so here we can also do read directory, write directory. So here we have, now let's create a write directory. And why I'm showing you this is because I think it always makes sense to kind of have a read directory and a write directory and to keep those separated, because if you merge them together, it becomes confusing at one point, particularly if you really work with an analysis over a long period of time. You do like 150 plots, 100 100 tables. It's getting really complicated. So it makes sense to have everything kind of subcategorized into folders with different names that are kind of logically consistent. And I also encourage you to develop analysis plans and use documentation practices that do make sense for your good analytic practices. I know for those of you who have done clinical research, like the GCPs, like the good clinical practices, I literally would urge you to also use like GAPs, like good analytic practices, like document everything, have analysis plan, accompany every analytic procedure, every analytic approach, literally step by step, and make sure that you have this all in. It's really, I have been part of many analyses, and I have done extensive analytic projects with a large number of colleagues. Everybody has ideas, all the ideas come together. At this point, I remember one particular one, that there was one of the statisticians from the NIH. There was an NIH-funded clinical trial, and with the secondary analysis, and like it became so many analyses, and he kept such a diligent analysis plan, documented every step. And I was in the end, I was doing the reading, and I was trying to go through all the analysis and have all this stuff together, because I was the first author on the paper, and I meant to keep an overview on all of this. And it was like his analysis plan was so helpful for me to actually find my way through all this analysis and kind of keep an overview, because it's like you may be sitting in front of 50 PDFs, 20, 30, 40, 50 Excel files. So it really makes a huge difference if you have a clear idea of what is contained in each Excel file. Otherwise, you need to sit down and like go through all of this yourself. Like it's easier to do the right from the get-go and to start documenting everything. Okay, but I'm rambling it up. Okay, good. So we are going now to write this into Write Directory. Write Directory, and the file name is what is it? mydata.txt. mydata.txt. We're going to separators. Okay. Oh. So now we have write.txt. Okay, of course that didn't happen because write.txt was also containing output. Always pay attention, every little detail. And this is one of the downsides of R. It's sometimes it's unforgiving, right? It just won't allow you to make mistakes because it will hold you accountable for all the mistakes you make. And this actually makes it kind of fun. Okay, so now we have this out. So now we're going to do the plots. The plots are we supposed to do here? Provide some. Okay, now let's read it first. So we're reading now. So the new read directory is now. Okay. Okay, so we do now read. So our df cars is read dot table read dot table. We're calling this read directory, and this is what was important. Stay consistent. Don't take the write directory because it's going in a reading direction. Don't call it write directory because it's, bluntly spoken, we're misusing the write directory now for a reading directory, just for the sake of this lab. So stick with the read directory. So the read directory, add output, because that's needed to get there. Get the paste again. Okay, paste. Output and output backslash on the slash output my My tab. .txt. So okay. DF cars. Okay, DF cars is out. Good. So now we have DF cars loaded back in. So now we want to do summary statistics. So summary statistics are easy to do, right? So you can always do summary. DF cars gives you summary statistics for all of your variables. Gives you all the summaries. You can also plot each parameter. So you do hist DF cars MPG gives an histogram of that particular parameter. So if you want to add now any kind of labeling, you do main equals histogram. And this is also how Bino and Marcel did it, histogram of MPG. Okay. It's not changed. The main, you can also do an xlab. Xlab equals xlab equals MPG. And that always changes the labeling of the x-axis. Good. So this is how you do histograms. You can also do box plots. Okay. So this is the example that Bino and Marcel showed. So they did here box plots. Box plot display a cylinder. Box plot empty cars. I'm not sure what this is going. This is just one. Okay. So if we do MPG as the cylinders, we can, for example, look into, so if we do MPG as a function of empty cars, cylinders, we see this as a function of cylinders, right? So it shows you actually different dimensions. So as a function of, we'll always render everything after the tilde, after the mathematical tilde here, kind of as a function of, meaning it will always automatically render everything left of the tilde as the dependent variable, so as the response variable, whereas everything on the x-axis will become the independent variable or the predicted variable. So this is how you create box plots, histogram summaries, scatter plots. Yeah, scatter plots is easy. You can also do scatter plots. Let's find a nice little, let's do hisp as a function of disp. Oh no, they do MPG as per weight. Okay, let's do that. Scatter plot is easily done as a by plot. That's the function doing a scatter plot. So you do my data, my dat, and no empty cars, or my dat. It doesn't matter. At this point, it's the same thing. But DF cars. This is all DF cars. Okay, plot DF cars MPG as a function of DF cars. My data. Sorry, I'm confused today. Okay. But this is how you plot. This is how you get a scatter plot. If you want to have in that now some certain features that are essentially valuable. So we can also do, okay, let's focus on this association between MPG and weight. I think this order P9. Okay. So we want now to create a fit, linear, simple linear regression of DS cars as a function of the weight. So now we put this together as fit ln df cars as a function of weight. So this is our fit. So if we want to look now into the summary, miles per gallon is significantly predicted by the weight of the car. Not entirely surprising, right? It should be an inverse relationship, which is true. So we see that. What else do we want to see? So we have now the plots, we have this summary, my fit, we've looked at this. If you want to amend now, okay, so now we can also show this as a plot. We can add on the plot appline. This will give us now the appline fitting through that. Essentially following the model. So this is the prediction of the model through that entire scatter. If you want to essentially look at the predicted value, you can create a y-hat that essentially is predict fit. This will give you now y-hat. So if we're doing now, so we want to add now points. Y-hat car equals green. We should be able to get now the green predicted points on there. So here these are the predicted points. Oh, wrong. Not that good. Let me do this again. Predict fit. Now we do my data weight, my data in PG, the y-hat as a function of df cars, because we didn't you get the gist, trend. This is what happened. Oh. 1 second. Like that. Just a second. Y-hat. Let's look quickly. What's going on here? Okay. Y-hat is MPG. Oh, wait. I think I have an idea. Not cross weight trend. Okay, so we do the plot, we do the appline, we do y-hat of fit into my point. Now we do this points here. Okay, but these are essentially our points. Okay, so we need to go further than that. We're gonna go plot with xlab, xlim actually extends or customizes the dimensions of each of your axes. So xlim actually gives you the limit for 50. Okay, go to this, airplane goes through that, go to this. Okay. So as you can see here, so the problem before was that I did not include the x-axis, which obviously doesn't make any sense. Then later, the problem was actually that I mistakenly took MPG instead of weight, which obviously doesn't make any sense. Yeah, long story. But now essentially we have entries, our predicted entries, our y hat in green for each actual entry. And this already illustrates what residuals are, right? So this is the actual predicted minus the actual value, the yi. This is your residual value. And this will essentially have a mean of 0 and will scatter around that mean of 0 with a variance sigma square. Good. But more about this in following questions. And yeah. So I think we're through all that you will need. Scatter plot, straight line is plot. Yes, you can. We've done that. Provide the interpretation. Well, that's easy, right? That's easy. And you know how to read that. So please make sure that you know how to read the output. Okay, let's go through this again quickly. So this is the actual formula. This is the formula that you have used. So again, it's MPGs as a function of weight. Now we have residuals here that essentially come with a minimum and a maximum. So they're not strictly normally distributed, also kind of reflected here by a median. So we said like the mean is 0. And as you know from introductory statistics, a deviation between the mean and the median implies a certain kind of skewness. $1 million question, the median is negative, the mean is 0. In which direction is it skewed? Yeah, it's kind of no-brainer. It's got to be left skewed, right? Because if it's pulling it, and outliners are somewhere on the negative that are pulling it. So this is interesting to some extent because the max is actually greater than the min. So there's actually, the tail actually extends further to the right than the min. But what you do have, you seem to have a certain bulk here on the negative, and we're talking about this here, right? So we're talking here essentially when you are doing yi minus y hat, your positives are these guys on top, whereas the negatives are here. So what you have here a little bit of clustering that you don't have here, but you have more extremes here on the positive. So this is how you have to interpret this. This is how you have to look at this. And then we have the estimate. So the estimate, this is the intercept, right? We did not centralize the intercept, which we could have done, obviously, as you have seen with the serum glucose. And then we have here the estimate for the weight. And this is the quote unquote slope. Then we have a residual standard error, which we know. So this is on 30 degrees of freedom. Why 30 degrees? Because we have two groups. It's 32 observations, two groups. It's n minus 1 for each group. It's that one that you can drop. So again, let's backpedal to the definition of degrees of freedom. Degrees of freedom is always from a group, those that cannot be changed or discarded. Whereas that last one that you essentially can drop because it's a resultant of your sum of squares and the actual number of entries, that last one, that n, where I equals n, that can be dropped, and you still can reconstruct that last data point by looking at the sum of squares, looking at the number of entries, and the sum of all the preceding squared deviations will allow you to essentially get to that last data point. So that's why the last data point is the resultant of the relationship between all other data points except for the last one. So from I equals 1 to I n minus 1. and the sum of squares. And the last one you can reconstruct, and that's why the last one you can drop. It does not go into the definition of the degrees of freedom. So it's always group minus 1, group size, group n minus 1. So if you have 2 groups, dropping 2 from both groups. So you have 32 minus 2. Same with the F statistic. Why do we need an F statistics? Because there's an interrelationship between an ANOVA, an analysis of variance, and the multiple regression or regression per se. That means that you essentially will determine your p-value on your F statistic. What does that mean? The F statistic means that you are doing essentially the variance between the groups divided by the variance within the groups. What does this mean again? So the variance between the groups is the deviation between various groups that we have looked at. If you have within the group, you also have certain variance. So this relationship between the groups and within the groups, that is your F. Just like you did with the ANOVA. You get this variation, and by that, so in an ANOVA where you have several groups, you want to see the deviation of all of the groups to one grand mean. And if this differs more, or if this differs to an extent that the F statistic is large and exceeding a certain critical value, critical threshold, you will deem this F value as significant, which is again based rather on the F table that you certainly have learned in introductory statistics. You're reading that from an F table, just like you did for a SEP statistics from a SEP table and for T statistics from a T table. You read from an F table that critical value, and the F distribution is essentially a unimodal right skewed distribution that essentially will be providing you a one-sided critical value. And as soon as your F from that multiple regression or from that ANOVA is exceeding that critical threshold, you have a significant F statistic. And this is this p-value here. So this is here, F statistic, this is your F. It's 1 degrees of freedom. This is the between groups, this degrees of freedom, because we have 2 groups, n minus 1. N groups minus 1 gives you 1 group, 30 degrees of freedom. Within groups, degrees of freedom, this is 32 individual n. So the n is 32 because it's 32 by 11 as a dimension. 32 minus 2 gives you 30 because 2 groups. 32 minus 2 groups gives you 30. That's the within group degrees of freedom. The p-value now smaller than 5%, far smaller than 5%, and therefore you have a significant model. How significant and how meaningful is it? Well, if you look at these residuals and this accuracy, that's going to be a pretty good model. So weight and miles per gallon makes a lot of sense, right? There's a difference if you drive a heavy Buick, heavy Chevy, as compared to, I don't know, smaller, like one of these little Fiat. So it makes a difference, right? So if you are now looking, okay, so we talked about the residual standard error, which is here, obviously not too large. And the way to quantify this is essentially the R squared. And the R squared essentially will allow for you to quantify your variability and to what extent you have an accurate estimate of variability. And what does that actually mean? Let me show you a slide. Let me show you a slide that you may find helpful in this context. And this is a slide that you likely know from introductory statistics. And these are slides where I have to give full credits to Professor Waldron. who is currently allowed to use these slides for various purposes. Okay, so here we have an R squared, and this is an adjusted R squared. And here at the very same time, we already have the distinction. So this is the formula for an R squared. Adjusted R squared is always smaller as compared to the regular R squared or the normal R squared. Why? Because it's penalized for the number of predictors. So how many predictors do we have in here? Only one. So the difference is marginal, right? But there is some form of a difference. And so what is the R squared per se? The R squared per se is nothing else but the explained variability in Y over the total variability in Y. And now you're going to say, hey, that sounds a little bit comparable to what we had with the F statistic. Yeah, and you're right. You're absolutely right. Because the R squared essentially is the effect size of an ANOVA. So you can quantify the effect size of an ANOVA by calculation of an R squared. And it's kind of the same concept. So if you remember the Anova table from introductory statistics, you essentially your R squared in there is the effect size, or your explained variability over total variability is your R squared. You have to is your effect size. And now you include information on N, which is your sample size, and the P, which is your number of predictors, and you penalize this relationship between your predicted versus total variability, then you essentially get to an adjusted R squared. So this is a penalized R squared. So now the $1 million question, which one are you going to use? Of course, the adjusted R squared. And you will make sure in your methods that you have used the adjusted R squared. All right, good. What else? I guess that's it, right? Okay, this interpretation of estimated model parameters in above question for Y intercept. Okay, so back to the basics. So intercept here, this guy, right? So where does that go through the zero? This should be somewhere at 37.2. So this is gonna break through the zero somewhere there. Then we have minus 5.334. So this degree is minus 5.344 with each unit. So from here to here, from this, from now, this, yeah. So from here to here, this is 5.344. Okay, okay. Anything else? I think that's it, right? Good. Good luck with the lab, and hope you had as much fun as I did. And good luck with the lab. All the best with it. Post to the discussion board. Please post to the discussion board. Let's have this a good conversation. Alrighty. Good luck. Talk soon. See you next week. Oh, you'll see me next week, but I hope to hear from you. Bye-bye.